So for 1.3 we need to show that a plus b to the power of n is equal to the sum of choose k among n times a to the power of k times b to the power of n minus k. So this is basically the proof of the binomial theorem. You can find several versions on the web. I chose the version that was the most clear to me. The proof is by induction. So proof by induction. So step 1, we need to show that it's true for n equals 1. And step 2, we need to show that if it's true for some n, it implies that it's also true for n plus 1. For n plus 1. So now we're going to apply this type of proof by induction to this particular problem. Step 1, for n equals 1, and so let's look at this complicated term here. Oh, by the way, it goes from k equals 0 to n. So sum of k equals 0 and n equals 1, so to 1, c kn ak b n minus k. Oh, sorry, actually we should replace all the n's here. ck1 ak b 1 minus k. So this sum has just two terms, the term for k equals 0 and the term for k equals 1. So we can rewrite that. For k equals 0 we have c01 a 0 b 1 minus 0, and for k equals 1 we have c11 a to the power of 1 and b to the power of 1 minus 1. So this simplifies. C1 choose 0, it's equal to 1. A to the power of 0, anything to the power of 0 is 1, and here it's just b. So we have b. And then C choose 1 among 1, it's just 1. A1 is just a, and b to the power of 0 is just 1. Anything to the power of 0 is 1. So we have b plus a, oops, plus a, and this indeed is equal to b plus a to the power of 1. So we finished step 1. We prove that b plus a to the power of 1, so or a plus b to the power of 1 is equal to this sum here. Now we need to do the step 2. So if we assume that what we need to prove is true for some n, so a plus b n equals sum of k equals 0 to n, c kn a k b n minus k. This is what we need to show. We assume it's true. We want to show that it implies, so want to show that it implies that a plus b n plus 1, so it's the next one, equals the sum k equals 0 to n plus 1 this time, c k n plus 1, ak b n plus 1 minus k. So we are going to try to decompose this. So a plus b to the power of n plus 1 is equal to a plus b times a plus b to the power of n. And we know what a plus b to the power of n is because we have the formula here, and we assume that this formula is true. So this is equal to a plus b, and we replace a plus b to the power of n by this formula here, sum of, so for k equals 0 to n, of the c k n a k b n minus k. Now we are going to distribute this summation here into the parentheses here. So this is equal to a times the sum. I'm going to use j instead of k here for convenience. So j equals 0 to n, just changing the name, nothing else. Cj n a j b n minus j plus, and now we distribute this sum over the b's, sum of, I'm going to keep the k's here, k equals 0, n c k n a k b n minus k. There is nothing complicated so far. Now I'm going to take the a that's here and put it inside the sum. So we have 8 times a to the power of j. That will be a j plus 1. And b n minus j, so it doesn't change. Plus I'm going to do the same here, take the b and put it inside the sum. So now we have b, and we'll have, instead of having n minus k, we have n minus k plus 1. So here there is a little trick. I'm going to define k equals j plus 1, or equivalently j equals, so this is equivalent, k minus 1. So now every time I see a j here, I'm going to replace it with k minus 1. So here, instead of having something that goes from j equal 0, it goes from k equals 1, right? Because k is just j plus 1. And it goes up to n plus 1 now. Because the last was j equal n, and now we have k, and so it goes to n plus 1. C, n, and j. We say we replace j by k minus 1. A k minus 1 plus 1, that will cancel out, of course, plus b n minus k minus 1 plus sum of, and here I won't change it, I will keep the k, equals 0 to the power of n c k n a k, and I will rewrite b to the power of n minus k plus 1 by using b n plus 1 minus k. So I'm just grouping the n and the 1 together. So this is equal to, I'm going to write this a bit more properly. K equals 1 to n plus 1, c, k minus 1, no change here, to n, times ak, because the 1 cancels out, times b, and b to the power of n minus k minus 1 is the same as b n plus 1, because minus times minus equals plus, minus k. And you see that's convenient because that will be equal to the b on the other side here. Plus sum from k equals 0 to n, c k n, ak, b n plus 1 minus k. So there is something that bugs us here. It's that here we have a sum that goes from k equals 1 to n plus 1, and here we have a sum that goes from k equals 0 to n. So what we're going to do is we're going to take the n plus 1 terms out here, and here we are going to take the 0th term, so take the first term in the sum and get it out. So if I take the n plus 1 term out here, it's when k equals n plus 1, so I have c n, and now k equals n plus 1, n plus 1 minus 1 cancels out, that's c n among n, a n plus 1, b n plus 1 minus n plus 1. That of course cancels out too. Plus, and now there are all the other terms here, so sum from k equals 1 to only n now, c k minus 1 n, a k, b n plus 1 minus k. So for the second part here, I'm going to do the same and take the 0th term out. So I have plus c 0 n a to the power of 0 times b to the power of n plus 1 minus 0 plus, and then I took the 0th term out, so I have a sum that goes from k equals 1 now to n, c k n, a k, b n plus 1 minus k. So I'm going to rewrite this properly. C, choose n among n, this is equal to 1. A n plus 1 doesn't change. B n plus 1 minus n plus 1, that's b to the power of 0. So that's just 1. At the bottom here, C 0 among n, it's 1. A to the power of 0 is all the 1. And here b n plus 1 minus 0 is just b n plus 1. So in the end we have a to the power of n plus 1 plus b to the power of n plus 1 plus, and we have two sums that go from k equals 1 to k equals n. So we can group them together and have a big sum from k equals 1 to n. In that sum we'll have c k minus 1 to n, a k b n plus 1 minus k, plus, and then we'll have the bottom part here, c k n, a k b n plus 1 minus k. So I'm going to take the a k b n plus 1 minus k here out of the parenthesis. I'm going to factorize. So I get a n plus 1 plus b n plus 1 plus the sum from k equals 1 to n of ak b n plus 1 minus k times c k minus 1 to n plus c k to n Let me rewrite this. So we were at a plus b n plus 1 equals a n plus 1 plus b n plus 1 plus sum of c k n plus c k minus 1 n times a k b n plus 1 minus k. Now we are going to use Pascal's identity. We know that this, we proved it for part 2, is equal to c k n plus 1. So we have a n plus 1 plus b n plus 1 plus sum of c k n plus 1 a k b n plus 1 minus k for k equals 0 to k equals n. So we almost have what we want here. The problem is, well, actually I made a mistake. K goes from 1 to n, so the only problem is that it doesn't go from 0 and it doesn't go to n plus 1. So we have to find a way to make these terms in the front equal to the 0th term of this sum and the n plus 1th term of this sum. So how we are going to do that? We are going to take the a n plus 1 and write it in a more complicated way, which is c n plus 1 n plus 1. This is just 1 times a n plus 1 b n plus 1 minus n plus 1. And this is also 1. So this is just the a that we wrote in a more fancy version. We do the same for the b, but this time we're going to take c 0 n plus 1, a to the power of 0, and b to the power of n plus 1 minus 0, which is b n plus 1. And then we have the sum for k equals 1 to n, ck n plus 1, ak b n plus 1 minus k. We just have to include now these terms into the big sum, which makes, the sum, and now we can write k equals 0 to n plus 1, c k n plus 1 times ak b n plus 1 minus k, which is what we wanted to prove. That to show that a plus b n plus 1 is equal to this. So this concludes the proof by induction. We could show that a plus b to the power of n is equal to the sum for k equals 0 to n plus, to just n, ckn times ak b and minus k. And here you have the complete proof of the binomial theorem.